So, for this part, you put a root here, you put a root here. So immediately, you have at least 2 roots at -2. Remember, a tangent is an even amount of repeated roots. So you could have at least 2 roots at -2, 1 root at 4. That's all you know so far. Where could the other roots be? Juliet?
Imaginary.
They could all be imaginary. So, this is 3 roots, so you could have 6 imaginary roots as the ending, and you're done. Or, what else could you have instead of 6 roots as imaginary? 4 imaginary, okay. And so you're saying 4 imaginary, well, where's the other 2?
Another 2 -2.
Another 2 sets of, or another 2 -2s, or another set of them. Because remember, when you see a tangent, it indicates that you have a repeated root, but it's an even amount. So it's not the number itself that matters. Again, this could be -7, this could be -1, it doesn't matter. It's the fact that you have 2 of them, and then you have 4 of them, or you could have 6 of them. Whenever you have repeated roots, the repeated roots actually almost come in pairs also. They always go up by increments of 2. Like an inflection point is either a triple root, a quintuple root, a 7 times root, a 9 times root, an 11 times root, okay? So again, the idea is that it's odd or even in the amount, not the number itself. So you could also have, instead of this, and then 2 sets of imaginary roots here. So you'd have 6 -2s, 2 of them imaginary at the end, and then a 4, totaling 9 still. Notice every time, 3 and 6 is 9, 5 and 4 is 9, 7 of them and 2 more is 9. What's the last possible solution?
8.
We had all imaginary already there.
8.
8 -2s. Have a 4 here, and then -2 8 times. Okay? Because again, the -2 must appear in an even amount. So 2 of them, or 4 of them, or 6 of them, or 8 of them. Same thing goes for the next problems. Let's quickly go through them. Let's quickly talk about them. For number 2, here we've got what? A double root at least. We've got 2 more here. So how many do I have already actually?
3.
3, but how many do I really have here? I see 4. Again, 1, 2, 3, 4 at least. Again, this has to be at least a double. Can't be anything else. It can be 4, it can't be anything less. So you've got 1, 2, 3, 4. There's 8 total. So the other 4 could be imaginary. 2 could be imaginary. 2 could be these ones again, the number 1. Or all 4 could be the number 1 again. Same idea. The last one is the little one that where you have the is the one you have the inflection point. What does that mean again? What is it? Triple root. Okay. So if that's not a triple root, what else could it be? Yeah, repeated roots. Do we not get this, or are you all just staring into space? Okay. So here, we know that whenever you have an inflection point from yesterday, the inflection point indicated that you have that root repeated. It can be repeated 3 times. It can be repeated 5 times, 7 times, 9 times. All those numbers are odd. So, right away I know I have at least 3 1s. I have 1 here at -2 also. So I start with a -2, and I write the 1 at least 3 times. How many roots does that give me? 4 of them. Again, I have a triple root here. An inflection point has to be at least a triple root. A tangent, the last example, has to be at least a double root. It could be more. So since you have a triple here and a single here, you have 4. Now, this was a degree of 8. So how many roots are we still missing? 4 more. So I know that those must be the first 4 roots. But here's my other options. So either, I'm going to show you the other options like this. Maybe it'll help a little bit. Either the last 4 could all be what? Imaginary. I could have 4 imaginary. How come it has to be 4 imaginary? Why can't it be like 3 imaginary? Imaginaries come in pairs. Again, where does that come from? How do you know that? Good. In the quadratic formula, we know what sign is there? Plus or minus. That's what indicates you have a pair. Okay? Complex conjugates or binomial conjugates. So, 4 imaginary roots. That's one option. So again, you would have -2, 1, 1, 1, and 4 imaginary roots. Or -2, 1, 1, 1, and what's another option? 2 imaginary, and then where do the other 2 go?
2 more 1.
2 more 1s. Again, see how the 1 has the inflection point? That means there's at least a triple root. There could be a quintuple root, which is 5. So how do you get 5 of them? You start with 2 1s, and then 2 of them could be imaginary. By the way, there's no last leg here. You don't even need that. What's the last option? 7. So you got 1, 2, 3, 4. Again, how come I know there has to be 4 of them there again? Because they come in odd sets. For this to remain odd, it has to be an even added on. Take a look. See how there's 3 here? To remain odd, you have to add even amount. 3 plus these 2 gives you the 5. These 3 here plus these 4 gives you 7. Again, no matter what, either you have all of them imaginary, some imaginary, and the rest repeated wherever it showed up, or you have one of them real, and then the rest of them all real still, without any imaginary. Now, tomorrow in your quiz, you're going to have something just like this, I'm telling you now. But keep in mind, what if you have an inflection point and a tangent? What happens then? What if you have an inflection point and a tangent?
Depends on the degree.
Good, depends on the degree, very good answer.
Then you can have 3 of one value and then 2 of the other.
Good. Or you could have 5 and 4, or 7 and 6. So again, if you had something where it's an inflection point, oops. Okay, I know already that this is going to be an odd degree. How do I know that this degree has to be odd? Good, the shape. Look at the shape of it. Doesn't it look like a linear function to you? It goes up on this side and down on that side? So it's got to be an odd degree. So you start by saying, okay, it's an odd degree, so I'm going to pick an odd number, 11. I could pick 9. I could pick 7. Doesn't matter. Here, at this point, it's -3. Let's say this point is 4. So how many roots do I have here at least?
2.
2 of them. How many points are here at least?
3.
3. Again, inflection, tangent. So I have at least 3 of these. So this is my starting point. I have to have 5 roots that way no matter what. Then the other 6 roots that are left, you can figure out whatever you want it to be. It can be 2 imaginary, 2 more from the tangent, and 2 more from the inflection. It can be 4 imaginary and 2 from the inflection. It can be 4 imaginary and 2 from the tangent. It can be 4 from the tangent and 2 from the inflection. It can be 4 from the inflection, 2 from the tangent. It can be 6 more from the inflection. It can be 6 more from the tangent. Notice the last 6, how many options? There are so many options here. So this would branch off into many different things. Again, the last 6 roots, they could all be imaginary. 6 of them. Or you could start breaking them up. 2 imaginary, 2 more from the -3, 2 more from the +4. Again, whenever you have missing roots, it's either going to be imaginary in sets of 2, it'll be 2 from the tangent in sets of 2, or 2 from the inflection in sets of 2. So you're always going to have an even number of roots missing. Again, this was the 11th, right? And how many do we have here? How many are missing? 6. Last problem, how many are missing? 4. Problem before that, I think it was 4, the one before that was 6. The amount missing is always even, because either you're going to have imaginary roots, which come in pairs, or you're going to have 2 more from this tangent, which is like a pair, or 2 more from this inflection, which is still like a pair. The additional roots always come in pairs. So you're always going to have an even amount missing. Okay? Again, if you need more help, please come ask. Don't just sit. Don't just let it go before tomorrow. Come ask after school tonight.
To get back our answer first, but all we have to do is just like look at the graph.
So all you're doing is looking at the graph. And again, the exponent will correspond to the shape of the graph. So if it's x to the 8th, it might look something like up or like down. Okay, because that's even think parameter. Okay, this really would be negative x to the 11th because it's going down actually. So that would really be the leading coefficient, but the negative doesn't matter. It's the degree that matters. So again, if it doesn't say x to the 11th, if it says the degree is 11, the degree is that 11 up there. Again, the highest exponent is the degree. So if a problem doesn't tell you anything about the actual exponent, and it just says the degree is, that's the highest exponent. That's the amount of roots. So, for today, if you want to, Before you leave, if you want to do it, write it over here. See if this works. If you put it on the other board, you do not have to. No. Oh, no, yes, you do. If you guys ever miss a makeup, you have to come in and write it on the next day if you want to come in and do it again. Your grades I posted last night, right around like 12 o'clock, so I know some of you didn't see it yet. So if you want to look today, go ahead and look today. Guys, it's just time when I get to do it, so it is. Late.
Late nights, early mornings.
Mr. Howard, what time do you wake up?
What?
John,
What time do you wake up?
too early. Too early. Too early.
I know a lot of people late nights in the studio.
All right.
Get an hour of rest.
Today's concept is very, very, very easy. Okay? All we're doing is graphing. We're using everything we've done so far, though. I made that up. You say.
You just say remember Reiki. I was like, that's
Right,
right people.
Right, it's not right like the real spelling. It's just an acronym to represent what you're going to do. So R will stand for the roots. Y will stand for the y-intercept. P will stand for a point in between the roots. And E will stand for behavior. That's Mr. Howard trademark there. Ashley. We're doing 36 today, we're doing 37 tomorrow, and then next week we'll do reviewing town. I'll remind you, don't worry. Talk about it today. You guys work on Monday, don't you? Yes. Tuesday review.
Are you done with
So again, this topic is review. It really is. And here's the reason why. When you're graphing these polynomial functions, it's as if you're graphing several quadratic functions together. Okay? It's as if you're graphing them next to each other. So the curve sketching, you're going to graph quadratics. And all you need to know is where are the roots, where's the y-intercept, just like quadratics, same steps. The new thing is that we're going to plot a point halfway between the roots just to show us how high or low the peaks go. The peaks and the troughs, how high do they go? Okay, the mountains and the valleys, if you want to think of it that way. And then the end behavior. The end behavior is very important. We have to know, does it go down like this? Does it go up like this? Does it go up like this? Or does it go down like this? Okay, we have 4 options here. 2 of them for odd, negative and positive leading coefficient. 2 of them for even, negative or positive and even. Okay? Now, for these 4 steps, I'm not asking you to memorize steps because I don't like to do that. I want you to understand all the things that are needed. If you want to remember something, you can remember that. But again, if you want to think about this in the conceptual meaning, think about what you need to do to graph. Don't memorize steps. So I know to incorporate or to capture a real graph, I need to know where the roots are. They're very important. I need to know where the y-intercept is. I want to know how high or low do the max and mins go along the graph. How high are these little humps along the way? And then what does the end of it look like? Does the end go off in one direction or the other? Okay, so those are the things that we've learned so far. So take everything that we've done for polynomial functions, the stuff like quadratic functions, and think about it that way. Do you guys remember how we found the axis of symmetry? And then we graphed the max or min, which we called the vertex? Okay? That's what step 3 really is. Because here's what I want you to notice. And I'm going to show you this before we get to an example. If I have roots here, here, and here, and I know that there's no repeating roots. Again, if the roots are repeating, we have to incorporate a tangent or an inflection point, all that stuff. And I knew that this was, let's say it was odd and a positive leading coefficient. I know already it looks like that. That's what odd and positive looks like. And I know the middle is going to look something like this for this to make sense, right? Yeah. Now, how high does this maximum go with this vertex? How low does this one go? You don't really know. That's why you do step 3. You plot a point halfway. So halfway between these roots, here's the point. If you can figure out what the y value is, you'll know how high it goes. if you can figure out for this x value, what is the y value, you'll kind of know how low it goes. It doesn't work out that it's exactly halfway though. Just like the vertex it was working out for the vertex for quadratics, halfway is not necessarily the min or max here. Okay? But it's a good stepping stone to see the curvature of the graph. So this is the goal for today of what we're going to do. Again, we'll have the y-intercept also. Okay? When the case comes that we have repeated roots or imaginary roots or inflection points, okay, so tangents, we're looking at, can we have them on the graph and still understand how to do this? So for example, if you knew that that was a double root, what does a double root look like? A double root looks like a tangent, very good. So if I know that it's a tangent, I know that it's going to be either looking like this, come back around, or it's going to look like this and come back around. Is that clear? That's what a tangent looks like here. Now, this one, there's none left. This one, John, whose did you just take?
What?
Whose is that?
That's
mine.
it.
Oh,
Put it
okay.
up there.
This indicates a double root again because it's a tangent. Now, how do I know which one to pick between green and red? From the formula, good. From the equations. So from the end behavior. If you knew that this was odd and positive, then this end has to go down. So you would choose this one here. Again, odd and positive looks like this. If I knew that this was even and positive looks like this. So you would be choosing this end now. Because even and positive, again, remember, looks like that, the general shape. So based on the end behavior, you'll be able to tell which way to draw your tangent or which way to draw your inflection points. Okay? So we're putting everything together that we've done into this topic. Remember, imaginary roots won't show up. So even if you have something like x to the 10th power, and say you had 6 imaginary roots, you're only going to see 4 on the graph. So it's going to be a little more difficult to graph those. Okay? Let's go on to the first problem. So, what's the first step again? Find the roots. How do I do that again?
The little table.
Very good. Synthetic table.
Right? Somebody have any O's?
Okay, notice nothing is missing.
O's.
Nothing is missing. I'm sorry? Okay. Run the 1 through. Tell me what you get here, guys. Some of you made mistakes on your quiz on the table itself. Be careful, okay? Multiply, add, multiply, add, multiply, add every time. People are doing it reverse. Oh, why do you look so sketchy then? You're staring at me like this. Write the question down, work on the problem. You done? Did it work? Did one work?
Yeah.
So get the next 2. Come on, there's 3 of them clearly, right? 1 by 1 is 1 and 4 is 5. 1 by 5 is 5 and 1 is 6. 1 by 6 and negative 6 is 0. Again, people,
I got one.
you don't need to rely on your calculator for this problem, I hope. Whoops. The roots turn out to be negative 3 and negative 2. Many of you got that, that's fine. But when you see that you can factor it, don't waste your time with the calculator, just factor it.
It's just easier.
Yeah, but you lose the fact in practice. Just practice. I could do that faster than you can type it in, I guarantee.
Done.
If it's factorable, you can easily factor it.
Sounds
fast.
like a challenge.
If it's not factorable, then sure, you have to go to your calculator. But factoring is much easier than it is to type in those numbers. So we've got, here's a root here, here's a root here, here's a root here. Agreed? What's the y-intercept? Negative 6. How come? Remember, to find the y-intercept, you make everything 0 for x. What's left? Negative 6. So the y-intercept is 0, negative 6. Let's write that down. I'm going to circle that also. So I've got the 3 root circled and the y-intercept circled. What did the P stand for next?
A lot of
The
midpoint.
points, right? The points. Where are those points located again?
In the middle of each consecutive.
In the middle of each consecutive root. So, we've got roots. Now here's what I'm going to do. You don't have to do this every time, but I want you to visualize this. The the number line, or the real number line, goes from negative to positive. So list like this. What's consecutive roots mean now? Because they're not really consecutive integers, you know that, right?
Yeah, like
They're consecutive roots. So these are consecutive, these are consecutive. So what's halfway between negative 3 and negative 2?
negative 2.5.
Negative 2.5. So I want you to figure out, if you plug in a negative 2.5 now, what do you get for the y value? And write that point down. If you want to use your calculator, you can. Just go to your table, put it in y1, put the original equation in y1, and go to your table and type in 2.5, negative 2.5. Okay, again, type this equation into y1. Type that into y1, please, and just go to your table and type in negative 2.5 for x. Yes, sir. 2.5 came from, we need to plot a point between the roots. What's between these two roots? Negative 2.5. What's between these two now? That's going to be a tough one. It's going to be a decimal, right? No, it's negative 0.5.
Oh, no.
Okay? But we're going to use negative 1 now, and we'll talk about why. Again, use your table function, people, because you're going to have to plug in another root in a second.
Oh, you guys are
It's
so
0.875. Let's go through this quickly. Everybody, y equals. Press y equals. Now, to use your table function, here's the reason you should do this. For this kind of a problem, you're going to have to do the table several times for other points. So instead of doing it by hand once, if it's once and you want to do it by hand, okay. Or you want to type it in the home screen, okay. But since we're going to plug in more than one point, write the function and then just use the table to find every point. So the function was x to the third plus 4x squared, squared, plus x minus 6. Okay, now I go second table. I notice, well, there's a 3 in my table. I'm not looking for 3. Just hit delete if it bothers you. Okay? Next, type negative 2.5. Hit enter. There's your number. Okay, 0.875. So go back to your screen here. We want the point, so let's list it. Negative 2.5, 0.875. There's my next point I'm going to use. So again, I've got 3 roots. I've got the y-intercept up top. I've got one of my points. Now, here's the tricky part next. And not tricky, but this is where here comes in your logic and thought processes. Halfway between these two is really negative 0.5, right? Negative 0.5. But aren't I already plotting something at 0?
Yeah.
The numbers between here are really 0 and negative 1. Agreed?
Yes.
And I'm already plotting a point at 0. It's called the y-intercept. So I'm not going to plot in negative 0.5 because it's so close to the 0. So let's use the negative 1 in this case. Again, does everybody see what I'm doing? I know these are roots here. I know the value of this is 0, negative 6. I don't want to use the negative 0.5 because it's so close to this point. It's not going to show me much. So I'm going to pick whatever else is left in there. So I'm going to use the negative 1 and plot it. So for the next point, let's use negative 1. And that's why in your notes I put plot a point about halfway. About halfway. It's not necessarily going to be halfway through. Okay? About halfway. So go ahead and plug negative 1 in. And for this one, either use your calculator or you can plug negative 1 into your synthetic table. It's very quick to do in that reason. You don't multiply. You're trying to find the, you know how in between the roots you have these little loops?
So I just curse
This,
out loud.
so it goes through the graph, comes back like that. I want to see how deep that goes. How deep that goes. Halfway between the roots, you're trying to do the if the root is here and here, the loop is going to look like this. I want to know halfway between how far down or up does it go. So we're finding the y value, so we can see the height of the function. Okay?
Yeah, I want to Oh, well. I'll check it out now.
Because, again guys, just to reiterate, you pick a point between these two roots here. There are several points to pick. John, you need to focus and stop talking. There are several points to pick between here. If you pick negative 0.5, that's exactly halfway. But we already have 0, because 0 is the y-intercept. So I just chose negative 1, so it wasn't so close to the 0. Okay? Again, what are we determining? We're determining how far does this loop go down. How far does this loop go down? So remember, in the beginning of the year, when we talked about functions, we said x is called the location. If you don't remember this, write it down. X is the location, y is the height of the function. Or we called x the width, and we called y the height. That's what we're doing right now. We're finding the y value so that we know what the height is. And just as a little preview, this is the graph itself. Here's the negative 2.5. There's that height that I was just talking about. The 0.875, this is 0.875 right there. This is the negative 2.5. So the width is the negative 2.5. The height here is the 0.875. We're finding how far it dips. That's what we're doing. Okay? So let's go back and put in our answer for negative 1. For negative 1, what did you get here? Negative 4. So there's the height of the function there. Now, I'm almost done. The last thing is E. What does E stand for?
Determine end behavior.
Determining the end behavior. Okay. What is the degree? 3, which is odd, and it's positive. So tell me, people, is it going to go up or down? Is it going to go up or is it going to go down? Come on, we have more than one answer, guys.
Down.
Odd and positive, you think of a line like this. Odd and negative, you would think of a line like that. But we have odd and positive. So this is what our graph will look like. So the end roots, the roots on these ends, see how there's a root here on the end, and there's a root on this end? From negative 3, we have negative 2, we have 1. This end is going to go down, this end is going to go up. That's already what the graph is going to look like. Again, the ends will go down and up like that. And if you look at the answer, take a look. From this root it went down, from this root it went up. Just like our sketch showed. Okay? So we're using everything we've learned again here. So, to graph this, let's go ahead and do it together before I go into the answer. What is your smallest root, everybody?
Negative 3.
Negative 3. What's your largest root? 1. Again, so you only care about maybe going to negative 3 and a little bit more on the graph. And here, the 1 really only matters. Everybody understand that? The roots really give you how far the function is going to go left and right. Once you get past the roots, it's just shooting up or shooting down. That's all it's doing. Okay? So that's what your graph can go from. I don't even care about the 2 again. Now, along the y-axis, look at all of your y values. Every y value, take a look, please. Which of these 3 y values is the biggest?
Negative 6.
The biggest.
0.
0.875. Which is the smallest? Negative 6. So maybe you want to go from 1 to negative 6, or let's go give it a little room on this time. 2 to negative 6. And maybe go, I'm sorry, go to negative 7, I apologize. Just to give yourself a little buffer. You don't have to label it all the way through. Again, this is negative 1 all the way down to negative 6. Give yourself a little extra room at the bottom. Now, please start by finding your roots. Okay, so we start with our roots. Easy enough.
Right.
Next, plot your y-intercept. What was that again?
0, -6.
Very good. Put your y-intercept down there. Notice, are there any repeating roots here?
No.
No, there are none. There's nothing repeating. So we don't have to worry about tangents, and we don't have to worry about inflection points. Is everybody clear?
Right.
Okay. No tangents, no inflection points.
What's with your socks?
So, with this problem here, we want to then take a look at the end behavior. Okay? Look at the end behavior. If we want to go to the points in between, we can go there in a second, but I'm going to hold off just for 1 second. Because I want you to see what the points will look like by default. The end behavior, we said. We took a look at this. We said it was odd and positive, so it's going to go up like that. So the left root's going to go down, the right root's going to go up. So go ahead. From the left root, go down. From the right root, go up. And again, it might not look perfect when you look at the curvature in a minute.
Does it have to be?
Second?
Does it have to be?
it's going to be at an angle. The angle will be dictated by the curvature of the graph. So if you have a deep loop here like this, the angle will go higher straight up. If you have a little loop here, it might go off. But it's going to be angled off, yes. Again, it's not going directly up or directly down, because then it would fail the vertical line test. And it would no longer be a function. Remember, to pass the vertical line test, the vertical line can only intersect once. If you had a vertical line, it would intersect infinitely. Okay, it would fail the test. So now, let's graph our points in between. -2.5 and around 1. So -2.5 is between these two and around 1. So there's my little max right there. Okay, we call that a local max, by the way. Calculus term, just so you know. It's called a local max because it's a maximum, but it's only a maximum in the area of it. Because this is like a max, right? Remember the graphs? But there is a bigger value if you keep going up. So we call that a local max because it's a maximum near its area. Down here, we want to loop down. Well, our point is -1, -4. -1, -4 is right here. Let's plot that. And what we're going to notice is, well, our loop is really going to pretty much go to the y-intercept. Okay? The -1, -4 was just a point to help me along the way. It didn't do anything more than that. Now, the hard part is this, guys. This loop actually goes down a little bit beyond -6. But without using calculus, there's no way to determine that value. It's actually impossible. Okay? You have to use something called the derivative. Now, what I encourage you guys to do is this. When you graph this, after you graph, look at the graph on your calculator. So, when I go to my calculator, if I can find it, when I look at the graph now, and clearly this is not a good zoom, so I might want to make my window, again, from, let's go, -4 to 2 to encapsulate the roots, and then, God bless you, from negative, let's say, 7 up to 2. Okay? And that's pretty much what we just graphed right there. Now, take a look. Look real closely here. Here's the y-intercept right there. Everybody see it? There's the y-intercept. If I can actually draw it here. Now, isn't it clear to you guys that that's not the lowest point, though? Do you see how it dips down still? So, this right here, that little pixel on the screen, is the minimum. Okay, and remember, we called that, I said a minute ago, a local min. Okay, this was called a local max. Good terms to know for calculus, please write them down. Okay, good things to know, so it's not new terminology. You use it in pre-calculus also. Now, again, this is the local min, really. But do we know what the value is of the local min? Not really. Okay? And there's no way to do it without calculus. There is one way to do it on your calculator, though. So if you really want to find the local mins and maxes, here's how you do it. You press, just like you're finding the roots, second, calculate, and then look at the function. See min and max? Just pick one of them. If you want a minimum, so if you want to find this down here, this location, you pick a min, because it's a min. So hit min, hit enter. It's going to say left bound, so go to the left of it a little bit. So maybe like right there, hit enter. It's going to say right bound, go past the min, go to the right, hit enter. Then it's going to say guess, just go in between somewhere, and hit enter. And again, you can always type in the numbers themselves. Look at that minimum. There is no way any of you guys will be able to determine this without using calculus. And you know what? That's sad to me, not for you guys, but the fact that we learn this and we start graphing this stuff, right? But we can't really graph every part of it. So when you move on to calculus, you're going to learn how to figure out these values. Okay, and it turns out it's actually very simple. It's actually a very simple way to do it. If we have time, what I'd like to do next week is maybe give you a preview of that. So I'll teach you that method, and it's very easy. It only takes us like 15 minutes to do it. But it's a new thing, and it's something you've never seen before. Okay, and I didn't do it last year, but I'm thinking about doing it this year, even though it's a little bit different. Okay, so again, we'll go over this next week if we have a little bit of time. It's a good thing though, Jason, it is. The fact that you're learning a lot of this stuff, remember the word concavity yesterday?
Yeah.
That's a word that you never even touch upon until you get to pre-calc. The fact that you guys learned that already, that this means concave up and this means concave down, that simple definition, it'll help you next year. It'll help Mr. Smith. And it'll help him a lot, especially when he's going over that stuff. You'll be able to say, oh, we know what this is already, we did that. And it'll make the lesson a lot faster. Okay? He teaches pre-calculus. Yeah. Okay. So again, that's the way of finding them in. Do we have any other questions on this graph? Okay, let's try the second one now. The second one I'd like to try, in your notes, by the way, guys, take a look up here real quick. The notes that I type up, I worked out all the steps for the first one. So I went through roots, y-intercept, point, and then end behavior. Everything is on here. Then after that, what I did in your notes is simply, the next four, I showed the actual graph. So if you want to practice some of these, I'm not going to do numbers 2 and 3 right now, just so everybody knows. I'm going to skip 2 and 3 right now. Everybody hear me? And I'm going on to numbers 4 and 5, because they have tangents and inflection points. So I want to make sure we get to those examples. Okay, so I'm going to take a look at number 4 now in your notes. So when you go back, if you want to practice these additionally, in addition to your homework, okay, you can go ahead and do that.
Do I have the answer?
That's what this is. The answer is right. It's not a solution, though, it's just an answer. Okay? Solution is like all the work. The answer is just the actual answer. Let's graph this function. P of x equals x4 to the fourth minus 2x to the third minus 3x squared plus 8x minus 4. And I'm telling you guys now, this is a tricky problem. Okay, so watch your little mistakes along the way. Don't fall into those mistakes. What do I start with, everybody?
Synthetic table.
Good, synthetic table. What do I test first? Julia?
Do you like Leonardo DiCaprio?
What does that mean? Like as an actor, do I think he's a good actor? Yeah, he's a good actor.
They were recording.
I think Catch Me If You Can is a good movie. It was one of his best movies. Nobody knows about that. Catch Me If You Can?
Oh, yeah, I read that movie.
Where he's a con artist?
I'm kidding.
I like it. It's your own opinion.
My
It's
sister
fine.
liked it, though. I don't think it sucks. I never saw it. I was just like,
Either way, it's your opinion.
Would you feel honored if he played you and if you were in
I believe.
Mark Howell. 1 minute, trying to teach class math. You won't pay attention. What will he do? His son, his film has not been remarried.
you never answered this question.
This film has not yet been rated. All right. So here's the key in this problem, and this is the thing everybody misses up on. If you look at this, you see that 1 is a root right away, right? Now, you still have left x to the third. Keep that in mind. So the resulting equation here is x to the third minus x squared minus 4x plus 4. And clearly, you can't find the roots without another table. So we make another table here. And it's 1, negative 1, negative 4, and 4. What do I start with now? 1. Very good. Good job. You got to start with the same root that worked. Because it could be what? It could be a double, or a triple, or a quadruple. So start with the 1 here again.
Then it's 0.
Gosh darn it.
Everybody see that?
Yeah.
So what do you notice?
It's a double.
It's at least a double. At least. It could be more.
At least.
Here's 2 roots. What equation results from this? This is the tricky part too here. X squared minus 4. Again, girls, please up here. When you bring this down, that's x squared. This is really 0x minus 4. Okay? Again, when you bring that down, this is simply x squared minus 4. Now, don't give me the answer, but tell me, what type of factoring is this called? Who remembers? We give it a name, so it's an acronym to remember. We break it up into 2 factors, and there's a special name for this.
A double factor.
Was it AC?
Not AC method. AC method is when you have an A value that's not 1. What are the factors? Anybody know?
1, 0, negative 4.
X plus 2x minus 2, right?
Right.
What did we call this? Because the middle terms would cancel when you FOIL it out. Difference of,
0.
Equation?
what was the word, Lauren?
With numbers.
Perfect what? Squares. Remember dots? Difference of 2 squares or difference of perfect squares. Whenever this is a square and this is a square, the square root is the result of each of these factors. Again, square root of each plus or minus. That's always your answers. So your roots become 2 and negative 2, which happen to be the same. And that's only a coincidence because they're opposites of each other. Remember, the roots are the opposite of the factors. So you really do have to switch the signs, but it doesn't matter in this
So
question.
the roots is 1 and 2 and
1, 1, 2, and negative 2.
Oh. Oh.
Now, I understand that the number 1 is the same number, and I'm writing it twice. Somebody explain to us, why am I writing it twice? Good, you know it's repeated, you know there'll be a tangent now. Again, you know there's a tangent at 1, it's an automatic. If John doesn't stop talking, he's going to automatically leave soon. It's the third time, man, come on, focus. Now, after you do the roots, you do the y-intercept. What is it, everybody? Good, negative 4, please list that. Now, we have a lot of points to figure out here. Everybody see that? Because between the roots, we're going to have, well, I'm sorry, we only have 2 actually, because one of them is repeated. So one of my roots is there at 2, one of my roots is at 1, one of my roots is at negative 2. So we need a halfway point between 1 and 2, which is 1.5. So let's figure out what that point turns out to be. What about over here? What are we already going to use? What's the point we're already going to use?
0.
We already have a 0, don't we?
Right.
So why don't we choose negative 1? Again, like last time. It works out that way, coincidence, okay? The halfway point here would really be negative 1.5, no, negative 0.5. Negative 0.5. Okay, but we're already plugging in a 0 for the y-intercept. So let's choose, again, this is the halfway point really, negative 0.5. But we already have a point at 0, so let's use a point at negative 1 now. So let's figure out those 2 values in our table. So again, go to y equals, type in this 4th order function, okay, 4th order, 4 powers. Go ahead and type in a negative 1 and a 1.5.
Isn't there an inflection and also
No inflection in this one. You're getting confused. I can see where you're looking at it in the graph. It's not inflection. What do I get if I plug in, let's do 1.5 first. What, around negative a half maybe?
Yeah.
4.375. There's your eighths, by the way. 375 is 3/8. So negative 0.4375. What about negative 1? When I plug that in, what do I get? 12. Thank you. Negative 12. Okay. Now, we have about 2 minutes before the bell rings. We're just about there. What's the end behavior? It's even and it's positive. Show me with your hand, please. Very good, Juliet. First one. Even, positive. Even, think parabola. Positive, think up. Even negative would be this way. So, when I graph my roots, remember these are my roots here? This is one root. This is another root. This is another root. The ends are going to look like this automatically. Everybody see that? Because it's positive and even. Positive and even, the ends go up. So you already know what the end looks like. Now, beyond that, we can graph the rest. Let's quickly do that. So again, I'm going from negative 2 pretty much all the way to 2. I don't care much beyond that. Along the y-axis, my lowest point is negative 12, so I'm going to show negative 10 down here, so I can see the negative 12 there. Okay, again, that's my lowest point. My highest point is, what is my highest point? The roots pretty much are the highest point. So I don't really have to worry about above the y-axis at all. Take a look at all of your points, people. Are any of the y values positive? So don't even label the positive y values. Who cares? They don't matter. Okay? So we know the ends go off like this. We just said that a minute ago because it's even and it's positive. There's one of my roots. There's my other root. Well, there's my 3rd root and my 4th root at the 1. And I know there's going to be a tangent there, don't I? But I still don't know what it looks like. Okay, let's plot the other points. I've got a y-intercept at negative 4. It's about here. I've got a point at negative 1, negative 12 down here. I've got another point at 1.5, negative half. That's right here. So for these to connect, they have to loop, right?
Right.
See this? And isn't this a tangent here? So let's connect these. Connect the tangent. Go down, bottom through the loop, and come back up. Again, I knew this point was here, so I had to loop through that point somewhere. And then I know this is a tangent. So as I approach the next root, it's a tangent. It's got to come back, go through here. Tonight, what I want you to do, either look on headline Okay? Well, look on that line tonight. Your homework, no copies were made this morning for an issue upstairs. All we did today, all we actually did was homework, example number 4 in class and example number 1. Okay, so look at the notes, try the other examples. Well, we'll look at the homework tomorrow. I have the homework. If you want to look at it, it's already on that line. So you can do the homework, but you don't have to. You hear me? Okay? You don't have to do the homework. You're doing every other example, not 1 and not 4. If anybody wants their makeups, they can come get them real quick on the way out, or come by after school and get them. Make sure your desks are in order, please, and your area is clean. Yeah. What time are you going to come? You going to sign up? Because I have book club from 4 to 4:45. Can you come before that? If you go by my room, try and sign up so that nobody else takes your spot. Okay? Be out of your way right now.